Discriminant analysis uses the training observations to determine the location of a boundary between the response classes. The location of the boundary is determined by treating the observations of each class as samples from a multidimensional normal distribution. Theoretically, we could fit an n-dimensional normal distribution to the observations in each class. This involves calculating the mean vector and covariance matrix for each class. These determine the center and shape of the distribution respectively. Having fitted the distributions, we could draw a boundary between the classes by determining the set of points where the probabilities are equal. Observations on one side of the boundary would be classified as one class, observations on the other side as the other class. We can do all this theoretically, resulting in an equation for the boundary that depends on the parameters of the fitted distributions. This means that we don't actually need to go through the whole process to perform discriminant analysis. We just need to calculate the means and covariances and apply the formula for the boundary. If we assume that the distributions all have the same shape, that is, the same covariance matrices, then the formula simplifies greatly. The boundaries turn out to be linear, and the coefficients of these linear boundaries are easily calculated from the individual class means and shared covariance matrix of the observations. This makes linear discriminant analysis quick and easy to perform. However, linear boundaries are not appropriate for all problems. If we do not assume that the covariance matrices are the same for all classes, the boundaries turn out to be quadratic. And again, the coefficients are determined by the mean vectors and covariance matrices of the observed classes. Quadratic discriminant analysis is therefore still relatively quick, although it does require more calculation and memory to evaluate, store, and invert the multiple covariance matrices, particularly when there are many predictors and classes. Because the boundaries are based on the statistical distribution of all the observations rather than individual observations, the boundaries are somewhat robust to noise in the training data.